Okay, so let's start again. I care about formal theorem proving. And as you all know, in formal theorem proving, we have access to almost perfect verifiers. And that means we can scale our inference compute. We can generate as many solutions as we want. And the verifiers will figure out the correct ones for us. And that raises a question, which is, which paradigm should we scale up? So we have now these reasoning models like O1. We have like search methods like AlphaProof. We have methods to decompose a problem into something hierarchical. And in this talk, I want to take stock of these different methods that exist in the literature and our own work on that, and to explain what scaling behavior has been observed so far, and which of these methods we should pursue in the future. So in other words, up there, these are the proofs that we're coming from in formal theorem proving maybe 1 year ago, and down there, these are the actual IMO level proofs that we care about, highly structured, many lemmas, many higher order ideas that have to be gotten right. And the question is which method allows us to do the scaling from simple proofs up there to the complicated proofs that we aim for. And so a few words about myself. I studied math in Freiburg. Then I got fascinated by formal theorem proving and methods in systems like Lean. And then I thought these are too cumbersome, and so we should invest a bit in machine learning for formal math. And that's why I'm doing my PhD now with Amaury Ayat at Ecole, with Gabriel Senef at FAIR, Paris, and in a collaboration with Timothy Gowers in Cambridge. So when I say scaling laws, I want to talk about exactly this, using more compute at test time on a single problem, and to observe your chance of solving the problem. So the metric we care about is pass at k attempts of solving the problems, k samples, and the chance that at least one of them is correct. And so I've brought you two famous ones from the literature. On the left side, there's code generation, where the verifiers by unit tests on the code. And on the right, we have board games, where you see a nice trade-off of training time compute versus test time compute. And so the general question that we ask when we talk about such scaling laws is not can we do that? Because in the limit, we can do everything. But the question is how much does it cost to do that now? And which methods should I be doing so that I can do it now and for 5 years? What is the thing that scales nicely? And so just to stress that point, these scaling laws matter and the coefficients also matter. For instance, on the here I've marked the factor in this law, which is 1.2, which means that spending more time on one of them is more beneficial than spending more time on the other one. And so these scaling laws matter, and that's also what we observed on theorem proving, for instance, in Lean, where I was determining the optimal model size at the time when we evaluated that, and it turned out to be 7 billion parameters, which was a good trade-off between quality of the model and speed of its actions. And that's something many papers do not study, but to get these things right is what matters in the end when you want to scale and deploy these systems in alpha scale scales. And so the literature has become a bit convoluted now. Everyone is inventing a method, explaining it, having their own setup with own data sets, own evaluation metrics, and it's become a bit convoluted. So I'm trying to take stock and organize it, categorize it a bit. And so the 3 dimensions that I want to compare are, so we can do proving at a line level, which is the classical tree search methods that we've seen in AlphaProof, for instance. Or we can do whole proof generation, where you just ask a language model to come up with the entire text of the proof beginning to end. Then on, I have no idea how this, okay. On this axis, we have execution. So this is the question whether after generating some code in a formal language like Lean, do you execute it and observe the effect, or do you simply say, this is my submission, please grade it now? Is there some multi-turn component where you interact with the environment instead of a one-turn interaction? And on the last axis, it's a bit fuzzy, but I want to make that point that there's different levels of test time reasoning. Is it more a fixed model that you just deploy, or is it more something that adapts more and more flexibly to the problem at hand? So this is, of course, a bit of like a fuzzy distinction, like there's no test time reasoning versus yes, there is test time reasoning, but I want to make this point that there's like different degrees of test time reasoning. And so we're going to go through these methods, and like some of the corners in this cube don't make sense or haven't been explored much, but we're going to go through the ones that I've listed here, and I hope that will put a bit of more clarity into like the space of like options that we have. So down there in the very corner, there's a code model, which is like the most vanilla, the most basic thing you can do. So you generate the whole proof, beginning to end. You do not execute it while developing it, but then you just submit it and you check how good it is. And so this leads to exactly the scaling laws that I gave you for code models there. So this is not a like proving, but a code model, but the scaling laws should be the same. And so if we want to analyze that, we can say, okay, there's kind of like n actions that the model takes. And let's say for each of them, there's a success probability, maybe p. And so you have an overall success probability of q, which is p to the n if they're independent. And so if you like want to know like what is your expected like number of samples that you need to wait until you get a correct solution, this is like waiting time will be 1 by q, so p to the minus n. And maybe more abstractly, like we can think of like a quantity h, which is my like minus log of the probability of getting the answer, which is an information quantity. So this is log k, and this is like the quantity that determines how easy or hard such a problem is. And so like from this like p to the n argumentation, you already see that there should be some kind of like logarithmic scaling involved. And people studied that more like more carefully, and they came up. So they used like different models and they used different data sets, and actually not all the curves look like just plain logarithmic, but at some point like they need to taper off because they're bounded by 1. And so they came to this law, which is the exponential of a power law. And this, so at first sight, like didn't make much sense to us, but like when we look at it from like this information theoretic perspective, like the information quantity of the problem as encoded by the number of samples that you need to solve it, log k, then you find out that like the distribution over those h, over those like information quantities needed to solve a problem is a Gumbel distribution. And that kind of intuitively makes a bit more sense now, because this is saying, so a Gumbel distribution is an extreme value distribution over like exponentially distributed samples. And so you could think of this maybe that there's like different directions of like a problem being hard, and like the maximum of those will govern like the overall hardness of a problem. In any case, just to say, so these are the scaling laws people observe in practice, and we have a kind of like heuristic explanation for why such a Gumbel distribution makes sense. So this is the scaling that you observe for coding models, and this is like the most, as I said, the most vanilla thing that you can do. Now coming to the other basic method, which is best first search. So this is a line-level search method where you generate your proof line by line. So if you have actions A and states T, then like you observe your first state, you produce an action, then you observe what happens in the next state, and you produce your action, etc. And so like this is just like factoring the probability of an entire proof by using the probabilities of the states in between autoregressively. But it is not reasoning about these. It is just like a clean way of organizing all these different like multi-line proofs that you can have into a tree. And so the important property here is, of course, that it's using the states. So you notice from interactive theorem proving, you can place your cursor somewhere and you observe a proof states. And if you execute one step, then you see the proof state change. And this should be important for the policy. And this is why best first search incorporates this knowledge into the policy. And you may think, well, why do I need to have this execution so explicit in the system? And the answer is, well, sometimes the proof states are not like this, but like this. So this is a long proof. And in this long proof, like you have all these objects and these assumptions about these objects that you need to like track in your mind if you want to do it by hand, and that like the system takes care of for you if you use such a formal theorem prover. And so like in such complicated long proofs, this is where it becomes important that we have to form a system that helps us, and we should use that help.
Sorry, and tokens are the whole sentences, or each symbol or something in the middle?
Sorry?
What are the tokens?
So on the left here, there's a like lean proof, and on the right hand side, this is like the proof state in one given line. And you were asking about tokens, so like if you use language models for that, you will just use a standard tokenizer that like the pre-trained model that you're basing yourself on is using. So that will be like some like subwords, like syllables. It's like the tokenizer isn't aware of the math, but it's also not important for these models to have a tokenizer that's super geared toward the language. Okay, so let's go to Monte Carlo tree search. This is kind of like the fancy sibling of best first search. And so roughly in this method, like this will always be deployed with reinforcement learning. And there, like we're gonna use, this is what you do when you solve a board game. So like it is this thinking, if I do this, they do this, I do this, I do this, okay. But if I did that instead, and they did that, and so on. And so what this does is it calculates a part of like this game tree in advance, and then it will distill this like knowledge gained from computing the tree back into the policy. So we can see the tree search as a policy improvement operator that's every time it's applied will slightly like push the policy into a better direction. And like in board games, like you would use the Bellman operator on like on the critic, on the value function, and you would use policy gradient method for the policy that suggests the moves. Now like the adaptation of this method to proving is called hypertree proof search. And the thing you need to like wrap your head around once is that like in formal proving, like proofs themselves, they are trees. So an induction proof, for instance, like would like decompose in a tree where like the induction hypothesis and the induction step are like different children, and like the proof itself will turn into a tree. And so proof search in such a system will be a tree search over such proof trees. And so HTPS, hypertree proof search, is exactly that. Monte Carlo tree search that is made for proof trees. So in Go, like a game is linear, a game itself is linear, and now we do a tree search over games. But in hypertree proof search, like the proofs are trees, and so we do a tree search over trees. And so this tree concretely, it is an and/or tree, so this is the meaning of hypertree. And at an AND node, that means that a tactic had several children, and all of these sub-goals need to be accomplished in order to accomplish the main goal. However, at every sub-goal, like you have choices, like you can apply different tactics, and you're good if any of them succeeds. So like at the sub-goals of a tactic level, there's an AND tree, and at the I apply different tactics to try to attempt to solve it, it's an OR tree, so it's an AND/OR tree. And so concretely how this works is like 3 phases: node selection, node expansion, and backpropagation. So you're gonna traverse down your tree until you reach a solving set of nodes. Then you're gonna expand that by asking the policy to suggest like new moves there. And you're gonna ask the critic how good these positions look. And then you're gonna backpropagate these like evaluations of the nodes up the tree, and this will make the evaluations of nodes higher up in the tree like more and more accurate, and these are the values we're going to train on in the end. Yeah.
What is the cost? How do you calculate the cost of every move?
Of a move?
Yeah.
I mean, like so an expansion is like where you use the language model. So like on each of these goals, we're going to ask for maybe 16 or 128 lean lines, tactics that we could execute there. And we're going to ask a language model on that state how good it is, and it will produce a sigmoid, like a float between 0 and 1, which corresponds to probability. So each of these expansions is like 128 language model calls.
How good it is in what sense? I mean, so you're trying to find this proof, right?
Yeah.
So you have to be able to evaluate if you're going in the right direction somehow.
Yes. So the critic just predicts like a solving probability, and these probabilities will be like accumulated at the parents also, and then like the value of an action is like the average value of the children of that action. And these average values will be used in the like tree traversal policy. So like the nodes whose children were evaluated to be more likely to solve the problem will be visited more often in the selection policy than the ones that were not deemed super successful.
Do you have to get all the way to the end of every tree to know if you...
So like at the original Monte Carlo tree search, it's called Monte Carlo because you would do like game rollouts. You would play against yourself and see who wins. And then you would say, okay, this is a 0 or this is a 1 or a -1. And then you would use that. But in like the AlphaZero version that like now everyone is using, like you're gonna shortcut that process by saying, okay, and from this point on, I don't roll out anymore, but I'm gonna ask a neural model for an evaluation that I'm gonna like backpropagate up. And this will be like in classical reinforcement learning, like a temporal difference that will make the value function more accurate over time. Yeah, so crucially, so as I said, so there's this action value that determines like for such a tactic action, how good it was deemed by the value model. But then also there's like this exploration bonus that's, that favors branches that haven't been seen yet. And so these two together make like the magic of Monte Carlo tree search, which is like exploiting in like looking at the parts of the tree that are deemed like way more like useful to successful play, but also trying like to explore everything else a bit, and so that you can actually find your move 37. Okay, so to summarize, hypertree proof search. In AlphaZero, you would have like an expansion would be always like one board position, whereas in proving, like you use a solving set of nodes. So you traverse down a tree, and like whenever there's several children, you take all of them until you have a solving set of nodes, and you expand them simultaneously. And like that, you make sure you always make progress on the proving and not just focus on some parts that may seem important, but in fact, like you're like being oblivious to the other parts. And in gaming, like you have like the symmetric thing with like -1, outcomes. Here in proving, like one player game, the critic produces solving probabilities between 0 and 1. And when you retrain, like usually like in AlphaZero, like you would say nodes that are above a certain visit threshold. In proving, you have even harder criteria you can also apply. For instance, only training on nodes that were proved, or even only training on nodes that are part of an overall proof of the root. And this is hypertree proof search. And this was done in 2022 at Facebook Research for Lean 3, and we modernized it for Lean 4, and it's like one of the most efficient methods for proving in Lean 4. Something I didn't tell you at the beginning on my little cube is on top of any method that you can come up with, you can apply like some sorts of like test time reinforcement learning or data augmentations that like will further boost the performance on top. And so this is especially what we tried in that paper. And so what do I mean by reinforcement learning at test time? So classically, reinforcement learning is seen as the training method. So you have a large problem set, and then like when you evaluate, like you take a very small like inference budget, and you're just gonna roll out the fixed policy that you have. But what you could also do, and this is reinforcement learning as a test time method, is you just throw in your test problems as if it was a training set. And you don't care whether you overfit to that or anything. You just like observe your cumulative solve rates. And in the end, you say a proof is a proof. These are the proofs I found in this time that I spent doing reinforcement learning on these proofs. And why is that a good idea? This data is, by definition, perfectly in domain. These are the problems that you care about. If you have like more than one problem in your reinforcement learning set, then maybe they can like benefit each other because they are from a similar distribution that you may not have access to at training time. And this is the like if you really only care about solving rates, then you should do as much learning as you can at test time. And so this is reinforcement learning as a test time method. And this is something that you can put on top of any other method, and this boosts performance. Here are our results with exactly that. On mini F2F test, which is a classic data set, we got like good, but nothing special, 41%. Whereas like doing like this cumulative like test time reinforcement learning method, we got one of the highest results by only using those 244 problems at all. No big pre-training data sets, nothing. And we did it in a very short amount of training compute compared to the competition DeepSeek prover and so on. And this is what we care about in the end, right? In the end, we care about, you give me some problems, I'm going to solve them with the compute that I have. These are my numbers. So obviously, like transfer to like new sets is important and so on. But here I want to make the point that if we really care about just like the highest ceiling, then we should use like all these tricks at the end, also test time. Yeah, and if you scale it up, probably like you get something like AlphaProof. And this is like marvelous work that produces totally unhuman readable proofs. We can of course look at them and they're not that bad, but it's nice to see that like this reinforcement learning kind of developed alien mathematics, but also it's hard for us humans to make sense of it. So in our work, it was important to put some like smart problem sampling, so active learning at the test time. In AlphaProof, they had another test time trick, which was a synthetic curriculum at test time. So they say the training loop was also applied during the contest, reinforcing proofs of self-generated variations of the contest problems until a full solution could be found. So they did exactly that, reinforcement learning as a test time method. And the 4 to 6 problems that they had weren't enough. And so they generated synthetic data augmentations so that they could actually do a reinforcement learning as a test time method. And lastly, there's some super cool papers out now, which is self-play for theorem proving. And there's a conjectural model that produces goals that look similar to the goals that we're currently trying to solve, or that are a lemma that might make sense in the context of the goal I'm trying to solve. And this is also exactly that. So this is a test time data generation, data augmentation technique, so that you can apply your test time reinforcement learning to enough problems that are close enough to the problems that you care about. OK, so let's further move through the cube. The next one is reasoning models. Reasoning models, you all know, this is models like O1 or R1. You ask a question in natural language, and they're going to produce super long reasoning traces that are kind of like thinking internal to the model. And then at the end, they're going to provide you like with a clean, rewritten solution of the answer. So the way it works is you just do end-to-end reinforcement learning from a base model that is not like used to giving you short answers or anything, with verifiable rewards so that it cannot be cheated, like proving, and like proving in a formal system. And what you get is emergent long chain of thought. So no one told these models to put longer chains of thought, to put longer reasoning traces. But this is just what happens over the course of training because it improves the performance. So one way to see that is that best of n, like majority voting, best of n sampling, you get n samples, you submit the one that was like appearing most often. This would be a method that the model could employ to get better scores. Probably the models are doing something more sophisticated, like we see that they backtrack, we see that they compare different things that they did and so on. So probably they're doing something better than just majority voting, but even pure majority voting would already allow the models to get to similar curves. And now we have like this application to formal proving, which is very nice by Numina team, presented by Jan this morning. So this is exactly the same idea. You have a reasoning model that is just told to like think for some time and then output the correct lean code. And the important thing is it was like supervised, fine-tuned on data where like the lean and informal reasoning is intertwined so that the model understands how to like develop such proofs piece by piece. And this comes with a super like strong supervised fine-tuning data set that they got annotations for, like for millions, as Jan explained. So the reinforcement learning here already starts at 62% mini F2F test. And then over the course of training, it goes up, not too much, but it goes up to 68%. And so the proofs, really like the R1 traces that we've also seen in informal math. So very long, detailed, sometimes with backtracking, like very verbose but human readable, and like we can really understand what was, or we can like a bit more like surmise what was going on in the model. And then it produces like these informal thoughts, but also lean proofs that here are on the other side, like the totally other side of the spectrum compared to AlphaProof, which is like modularized into many, many tiny steps, each just marginally more than what you knew before. Each of them like very carefully proven to make sure that like nothing breaks. Also very verbose. These are the kinds of proofs that you get from such reasoning models. And so the numbers look great, like Jan presented them. But I want to add like two notes to that. So it's a 10 times larger model. It's 10 times longer answers. So like if you look at the total compute cost, the curve is kind of shifted a bit. And also we have to see whether like this great work on data annotations and data engineering, whether how it translates to the other methods in this graph so far, because we don't know how much of a boost like those 20,000 handwritten SFT samples on IMO style problems would give you. So this is great work, and we want to see like after the summer when the model was released, how like the different pieces here, like larger model, larger reasoning trays, better data set compare if you apply them similarly to other methods. So what's the rationale of doing reasoning models? Simply, informal math models are way stronger right now than formal math models, and the reason is simply it's another scaling law, the availability of training data. There's way more informal math data than formal math data. But of course, no one forces you to do a pure reasoning model, like hybrids are conceivable. And this is, for instance, like the classic draft sketch proof, or like sketch-based proving as we call it, where you have an informal proof, which may be given by the human user or may be generated. And then you first translate it to like a sketch of the proof, which has some holes, and then you can fill in those holes either with a classical automation tool or with a stepwise prover, maybe a tree search prover. And so how does this look in practice? So this is a problem from the ProofNet's proof translation database. And there's one trick involved. Like, so the statement is every Boolean ring is commutative. And you have to come up with the trick of like applying like this Boolean property first to minus a and then also to a plus b. So there's like these two little like pieces of trick involved to getting it right. And these are proofs that the classical tree search methods like MCTS, they struggle with, because they have a hard time coming up with a lemma that may turn out useful later. But if you have access to the informal proof, and if you translate that, it's super easy. So here you can see like a GPT-4o translation in the have statements. So like everything that is like higher order, the pieces that are taken from the human written proof. And then in the indented parts, you have like a hypertree proof searcher that was filling in the proof tactics bit by bit. And so here you have a nice example of how like these two like levels can like play together nicely, and this is work in progress on our side. And so such problem decompositions, they've also been used by like the current like leader model kind of DeepSeek Prover v2 for their initial supervised fine-tuning data set. So they have a large model that decomposes the problem into this sketch. And then since the large model was not great at proving because it hadn't seen much of lean, they used like the previous iteration, like a small model that was filling in those lemmas bit by bit, and this produced their initial data set. We wonder why they didn't like pursue this approach up to the end of like just deploying like a two model system. We don't know the answer why they didn't, but at least for the initial SFT data set, they were using this like decomposition approach, and I'm going to talk more about like problem decompositions later in the context of code. Okay, so to compare, like there's like these reasoning models. These are no execution. They produce their code. They produce their informal reasoning. They produce their code, and then they submit without like interacting with lean before submission. And on the other hand, like we have like these methods like best first search, MCTS, or the one that I'm going to talk about in a bit, which use the interaction with the environment, which use the lean. And that's a kind of like fundamental like philosophical question, whether you want to have execution in your setup or not. And so this is what is called word modeling in the traditional like RL literature. Like, do you want your model to model the transition dynamics of the Markov decision procedure, or do you want to use the actual environment for that? And so like, the case is to be made if like the capacity of the model is large enough, then it's always beneficial to code train on this word modeling task, so that instead of just predicting state action, you should always predict states, then action, and then the next state, because that tells the model some useful information about like how the actions actually lead to effects in the environment. So like this is what like most of the tree search methods ended up doing in the end. You always train on proof state, tactic, next proof state, even if later, when like using and evaluating your model, you only use the part state, proof state, tactic. So this is a pure code training task, but it's meant to like improve the representations and put some useful information to the model. However, like if like the actual environment is cheap, there's no clear reason for not using it at like training and test time. The original environment will be always more precise than any like neural approximation that we can make for it. And so even though in principle we could, instead of like using the official environment, we could use like a neural model of the environment, like what was done in mu0, for instance, or in Iris, which is the same with transformers for video games. So we could use a simulator, like a word model, to do our reinforcement learning. But it's not clear why we should be doing that if the simulator wasn't any cheaper than the actual environment. So clearly, if you train a robot, for instance, or Mars rover, like it may be super costly to test that in the actual environment. And so you have to resort to simulators. But if your environment is cheap, there's no clear reason for not using it. And so like I would make the argument that all these reasoning models, instead of relying on the fact that they would be more or less accurate at executing lean kind of internally, we should give them the access to the formal system so that they can actually interact with the environment also at test time. And so that's maybe more a point for the discussion. So reasoning and planning, maybe it kind of takes place in unsound logical quotients of the actual logical system. So there's a case to be made that like the informal language is super important because it allows you to do that. But it's not clear whether like whether the simulator allows you to do this sort of reasoning in unsound logical quotients, or like what kind of training we would have to do for this environment modeling task to actually focus on the important parts of a mathematical argument and not on the unimportant parts of the mathematical argument. That's like a kind of like open-ended question on whether we could make an environment that would allow us to train on something like that. But long story short, I want to advocate using lean execution, and so I want to advocate instead of using reasoning models, like what I call a multi-turn model. And what that is simply the idea that if you have written some lean code and you execute it, either you have success or you get an error message. So here the error message says tactic rewrite failed, did not find instance of the pattern in the target expression. So I can read this and I can try to understand what happened. And error messages, they are supposed to be useful. Like people like put effort into producing this error message so that I could improve my code. And so if that is really the case, we should use them and we should fix up our code and retry. And so this exists as a supervised fine-tuning method in Lean today. So nice paper Malot's multi-agent chain of thought reasoning in Lean. And it exists as a reinforcement learning method, but only in code, so only in Python. I'm going to present you the scaling graphs in Python, and we're going to hope that it will also translate to Lean later on. So this is a paper from our team which studied exactly that. So you generate a piece of code. You're going to execute it on some public test cases. You're going to observe like errors, that's like syntax errors, runtime errors, or like whether the public test cases failed or not, like expected output versus actual output. And then you have a certain number of retries in which you can fix up your code and see whether it gets better. And this is compared on like a fair comparison. So in methods that have more turns, you have less attempts. And so the dashed lines are the instruct model, the untrained, unreinforcement learned model. And you see the classical like logarithmic scaling regardless of the multi-turn number that you're using. If you do reinforcement learning with a single turn, you get like quite well improved solve rates in Parset 1 or in Parset 10 here, but you get a very worse slope. So these models are very good at like exploiting what they know, but they're not really good at like staying diverse and like finding solutions if given many attempts. And so finally, multi-turn models fix that. So multi-turn models, they have like the initial diversity, and since they do not need to collapse onto something simple that works for them, because they have the opportunity to fix up the initially maybe slightly wrong solutions later on, they have the same scaling behavior as the original instruct model, which is not the case for many reinforcement learning methods. And so this is a really cool finding that like with the multi-turn modeling, we do not just get like this new capability of fixing up errors, but also we get like the scaling behavior that we would like to have when we care about tough proofs. Okay, and to analyze that, like just a very simple heuristic argument to make that point. So assume we have n independent decisions to make, and each of them has a certain success probability p. Then, like if you just sample, then you have to get all of these right. And let's say they're independent. So we have again like this p to the n overall success probability. So we need this 1 by p to the n number of samples. But in iterative refinements, in the best case scenario, oracle fixing means that like we observe the first error, and we always fix an error if we see it. And in that case, the number of samples that we need is just the expected number of errors in our code, which is n times 1 minus p. So like we go from horrible exponential scaling to something like linear, which would be a great improvement. Although like this is only like in this toy example with the oracle fixer that can always manage to fix something. But so it's clear that like there's a deep improvement if you use your feedback and if there's a certain chance of like using your feedback correctly. Okay, so this is the space of algorithms that we've covered so far. The classical line level proof search, best first search that was being done like 3 years ago. Then like the Monte Carlo like AlphaProof version, which uses these train value models that can get you like a more adaptive reasoning in a test time. Then the reasoning models that are like en vogue now, which produce long chains of thoughts and leverage informal reasoning. And multi-turn models that we yet have to see for lean, but which I think is a promising way forward, which combines like the best sides of MCTS and reasoning, which is like informal reasoning plus execution. Now I promised I want to talk a bit more about like these problem decompositions because it seems very important to mathematical proving. So I mentioned informal math. There's you have lemmas by which you can decompose mathematical problems, and this is like a nice encapsulation of a certain property. In coding, like the encapsulation method is functions. So we can write code in a modular fashion by putting several functions one after the other and implementing these separately. Now we wanted to study like this sort of behavior where you have first something that decomposes a problem into subproblem, and then something separate which implements these pieces piece by piece and recombines these solutions later on. And so to have like a task where we can study this well, we use code actually because it needs less engineering to like get started there. And so the idea is like, you know, this combinatorial explosion of like your chance of making a slight error, but we can fight this combinatorial explosion with our own combinatorial explosion of like recombined solutions. So this makes sense if generating something on your GPU is super expensive, but executing something on the CPU is cheap. And so here in coding, for instance, usually you get M full solutions and you can evaluate M full solutions. But if you do this hierarchical modularized generation, say you have n functions that you're implementing with k implementations each, then you got n times k calls to your language model. But you can execute all combinations, which is k to the n. So under the assumption that the execution is cheap, or like we can disregard it, like we can have lots and lots of like samples that we can evaluate later on based on a very small number of GPU forwards that we did. And in proving, of course, it's the same because like we can even like evaluate the parts separately, maybe because like a lemma can be checked independently by Lean. And so here we wanted to study like this dynamic of we have one part that decomposes a problem and another part that's, that tries to solve the problem, and how we can jointly learn these two components in a reinforcement learning fashion. And so what we found is a quite interesting finding, which is like our biggest challenge is interfacing friction. So like maybe you know people who don't like to work with colleagues because if they hand some of their work to the colleague, they're never totally sure whether like it will turn out correct. And there will always be a bit of like, or maybe some of you have worked in teams where like you split up the work and then like in the end you find out that it doesn't like work together because like you had some interfacing issues with how you define things. And this is exactly what happens in our case. So if we reward the entire system for its average pass at 1, so like we have all these combinations, we evaluate them, and then the average of these rewards is the reward the system gets, then the decomposer will say, no, I think you guys, you implementers, you have too much interfacing friction. I'm going to shrink the number of functions that I want to have implemented, because in that way, there will be less friction between the different implementers, and there's a higher chance of overall success. And so with standard reinforcement learning methods, like GRPO, classical pass at 1 optimizing methods, like we see that the size of the decompositions goes down from like 4 to 5 to 2 or even 1, which is like removing all the benefit of the method. So we had to deal with that, and our solution was, well, actually we don't care about average pass at 1. What we care about is in this whole attempt of k to the n combinations, whether there's at least one of them correct. So like now we want to reward with something like the overall solve rate of the method, or with pass at k but for a very large k. And so we managed to cast this as a kind of like reward transformation that applies a utility function to the actual reward. And so with like interpolations between the mean and a max, like soft maximum objectives, we managed to stop this decay of the decomposition size. So that's the runs you see here. And we got way better results. And so here, for instance, on the left side, I'm plotting the success rate at 10 like such decomposition attempts versus the success rate at 100 such attempts for different runs. And you see that like there's no clear relationship between the two for the different runs that I plotted. However, like what is way more predictive, and that means that like these runs, they all have the same like pass at 10, but some of them perform way better at pass at 100 than others. So we were asking ourselves, so why is it that some of them perform way better than the others? Like, what is the secret scaling that some of them have and some don't? And the answer is, like, what predicts like the scaling is the average number of functions that these methods use. So only if you actually like use this combinatorial explosion well, then you're going to have a good pass at 100, although you do not see this advantage at pass at 10. So this is also something to be aware of, that some methods, they only work when scaling, and to like make the point about pass at 1,000 and 10,000 and so on. But so we see like there's like this delicate interplay between the decomposition method and the implementation method. And more precisely, this is a question of like multi-policy training. Like we have like these two functions that typically we represent by the same language model. But like language modeling or like maybe deep learning in general works best if either you're a single task, like you train on exactly one task, or you're massively multitask, so you train on all tasks that you can think of. But what is harder is like this two task, like bimodality or something. And that's where like deep learning has come up with lots of like tricks, like exponential moving averages, alternate training, and so on, to stabilize these sorts of setups. And so in our case too, like we found that like this two policy setup is a very unstable one. So joint training, what is like the naive thing you would do, like you train both at the same time, doesn't work at all. It's also like proven that it may not work. Then there's something alternate training, like first you train one policy by keeping the other fixed, then you train the other by keeping the first fixed. So this ought to work, like it's proven to work, but in our case it doesn't. What works best right now is separate training. So you train each policy against a fixed like base model for the other policy. And then you recombine policies that have never seen each other, which is totally unprincipled, but works best. So like this is definitely work in progress. Like we need to understand what makes such like hierarchical multi-policy training work in practice. But we can say already that this may be like a challenge that needs to be overcome if we want to do something like the DeepSeek Prover v2, not just for initial SFT, but also as an ongoing reinforcement learning task. And maybe I'm hypothesizing now, maybe that was the reason why they stopped doing like the 2 policy training and went for the 1 policy training in their setup. Okay, so to summarize, I think one of the most exciting properties about reinforcement learning for math is that you have access to this verifier and you do care about like the tail. You care about like the path at k for super large k. And so that's where like your reinforcement learning problem becomes essentially an exploration problem. And this is something that hasn't been studied. This has been studied a lot. But for language models, maybe it hasn't been studied enough yet. And so we have like this list of tricks that I mentioned over the course of my talk. So in AlphaProof, the synthetic curriculum that they just generate a testing time. In self-play theorem proving, the conjecture that also generates such a like test time data augmentation. In our Able, the active learning component of how you sample problems in your reinforcement learning at testing time. In DeepSeek Prover v2, this cold start data of problems decomposed into lemmas and leveraging this combinatoriality. In our project on decomposed code on multi-policy training, on like when I mentioned soft maximum objectives, like these reward transformations that allow you to formulate reinforcement learning objectives that are more meant for exploration. So these are just some examples of the things that people are doing if they care about reinforcement learning for exploration. And I think like this list could go on for quite a while. And I'm very happy to see in the next years to come which methods allow us to do like reinforcement learning at large scale, focusing on the exploration part, like solving the hard problems. Thank you so much.
Questions?
I have one question on the multi-turn. So you had several turns, then I guess the limit is to do directly reinforced learning with this execution feedback, or
you mean the multi-turn in the cube here?
Yes. Why just do only like just a few turns, or can you just can't you do the reasoning model directly with some execution feedback?
Yeah, basically like I think what the reasoning model is missing is just the option to submit a piece of code, get the lean answer, and then continue. So this is just what I'm saying, like this is the part that it's missing currently. Where do I have this actually? I skipped that before. Okay, nice. So like for instance, like we see that for proof sketch generation. We had some experiments where we generate up to 1,000 attempts in up to 5 turns of fixing yourself. So this is not full proofs, but it's only proof sketches which are allowed to contain holes. And so these hyperbolas here, these are the ISO compute curves. So number of turns times number of attempts is constant, which is like a fair comparison. And so if we follow this line, for instance, like we see how it goes from like light blue all the way up to like some dark blue to pink. And so like actually like the performance goes up by around 10 points if you go from like a pure like 1 or 2 turn to a 4 to 5 turn. And that is like compute controlled because we followed the line. Yeah. Yeah.
I do have a very naive question because you mentioned like to justify the interesting aspects of using the execution feedback that debuggers provide with interesting messages that you might as well use, like they're meant to be useful. I haven't had the chance to work with Lean, but I mean it's pretty known that for debugger it's really hard to make super useful messages. Are they like reliable enough that they're actually useful?
Okay, so two things I can say for this first one. In this reinforcement learning from execution feedback that I explained as the code version, they use a funny baseline which is random feedback. So they're just like mixing up the feedbacks across attempts, and they see that like it actually leverages the feedback and not just uses the opportunity to do multiple turns. So the random feedback is way worse. Second, for Lean, I would say that actually like in these systems that base themselves on dependent type theory, it's actually way easier to get good feedback than in an average compiler. In an average compiler, like either maybe if you have a syntax error, fine, you can point out the exact syntax error. But if you have a semantic error, you just know that the code ran, but it produced something wrong. But in dependent type theory, everything that is semantic is kind of like mapped back to syntax. So like if you apply a hypothesis to like a theorem where it doesn't apply, then this will not pop up as a like random runtime error, but it is a syntactic error to like do this semantically wrong combination. So actually, I think like the whole appeal of like dependent type theory is to give you lots of like feedback of what terms to provide and like what you did wrong when you try to like provide the wrong term.
So in this framework of formal math, is it possible, has it happened that you can find new theorems, or is it about verifying already known results?
I mean, like all these benchmarks that we're working on right now, like they work under the like supposition that there's a formalization of the statements, and then you want to provide the proof, and for proofs we have verifiers. Now there's like people who say, okay, like we need larger data sets, so we're gonna like look for mathematical problems, and we train models to translate these problem statements to Lean. But this is a process that we cannot supervise exactly. Like we have to manually inspect, or we have to like rely on some metrics that we computed whether like this statement formalization is actually correct or not to begin with, and then you can get proofs for these or not. So like and since right now like we're not data constrained in any sense, so like the distribution of like math that is informal but online is super large, and so right now like I think it's still just about like working through that trove of math that we already have and like making most use of it. But if you have like a conjecturing system, like in the self-play theorem prover, nothing would stop you from having something that produces a statement and producing a proof. However, like I think we're far from the state where like this will produce any statements or proofs that like people would be surprised or interested about. Like this might be like a nice lemma that is useful in the context of the proof that you want to do, but nowhere else.
Right, because it's complicated to know if something is interesting or not.
Yes, we have to ask Katie for that.
Okay, thank you. Any more questions? If not, let's thank.
Thanks so much.